All right, welcome back to another episode of Science with Surback. Today what we're talking about is section 13.1, which deals with work, power, and machines. And before we get into the details of notes, I just want to outline a couple of objectives that you should be able to meet by the end of this video. Objective number 1, determine how work is calculated. Objective number 2, identify the relationship between work and power. And objective number 3, be able to describe and determine how machines make work easier. So let's go ahead, let's start out with the definition that we have for work. Work is defined as the transfer of energy to an object by the application of a force that causes the object to move in the direction of that force. Now, work can be calculated by multiplying the force by the distance over which that force is applied. In an easier and simpler way, we can have a formula to express what we have with work. And that formula is force times distance. Now, work equals force times distance can also be shown as a capital W equals force times d for distance. Now, with this formula, each of these variables have a unique unit. So the W is standing for work, and it is in the unit of joules. Now, F is for the force, and it is in kilogram meter per second squared, or you could call this same unit 1 Newton. And then the D for distance is going to be in meters. Now, this is an important note, is that when we have work, or when we talk about this business of work, the force used to calculate the work must be applied in the direction of the object's motion. So what we can think about here is, okay, well, what happens if we don't have an object that is moving, or a non-moving object? And so what we need to think about here is this. If a force is applied to an object which causes no movement, no work is being done. Now, let's go through 2 examples where we can apply this. So, example number 1 is going to be you trying to lift a car up. So let's say you're on that back bumper and you're trying to lift up on the car, and you may apply a large force as you're trying to lift up that car, but if the distance that the car moves is equal to 0, the work done on the car is also equal to 0. Again, the key thing here, distance of 0 means work of 0. Again, distance 0, work 0. That's key here if you have to talk about the work. Now, once the car moves, even a small amount, so you apply that big force there to lift the car up, you have now technically done some work on it. Now, our second example that we have here is this: a weightlifter holding a barbell over their head. So again, this barbell is already over their head, and so we have to think about this. The barbell over the weightlifter's head is not moving. So since the barbell is not moving, no work is being done on the barbell. In other words, the barbell is stationary, no movement means no work. Okay, so the key here is that for an object to have work applied to it, it has to be in motion, or it has to be moving here. So let's transition now how we can actually utilize that work formula and actually go through a particular calculation of work. So we have our steps to calculate our work, and the first thing that you need to do is write down the formula for work. So remember, that formula is W equals force times distance. Now, work is what the W stands for, and it can be in units of joule. But for work, we can actually express the units in a couple different ways. So one, we can have 1 joule, which we say just a J there. This is equal to what we call 1 Newton meter, so 1 Newton times meter there. And this can be also equal to 1 kilogram meter squared second squared. And now on force, we can have units of newtons or kilogram meter per second squared. And then the D for distance is going to be in meters. Once you write down the formula, you're going to determine the known values of the problem. And now it's important to include units in this particular step. Once you have done that, the next step is determine any unknown values for the problem. The fourth step here is to insert the known values into the formula for work. Step 5 is to solve mathematically to determine the unknown value. The sixth and very important step is to include the correct units in your answer. And now remember, in step 1, we listed all the possible answers for each and every one of those variables. So let's go through and let's solve a problem using the work formula. So we'll transition here to our example problems, and we have this. We have a crane that uses an average force of 5,200 newtons to lift an object 25 meters in the air. How much work does the crane do on the object? Okay, so what happens here is this. We always write down our formula. So got ahead of myself. Work W equals force times D for distance. So we list out all of the variables. So W, our F for force, and then the D for distance. Now, it says in the problem, how much work does the object do? So this becomes our question mark. We don't know. The force, it lists the force at 5,200 newtons. And if you look back in step number 1, that is the correct unit for force. And then the crane is lifting that object up 25 meters. So this becomes our value for distance. Now all we're going to do here is we're just going to plug these values back into our work formula. So work equals 5,200 newtons times 25 meters. So in our calculators, all we need to do is we need to put 5,200 times 25. So 5,200 times 25, we press enter, and we get a value of 130,000 for our numerical portion here. So work is 130,000. And remember, if you look back on the correct units for work, it would be in J for joules. So that would be our answer there, 130,000 joules. Now, second problem here, a little bit more involved, but a mechanic uses a lift to raise a 1,200 kilogram car 0.5 meters off of the ground. we want to know how much work does the lift do on the crane. So again, running out of room here, but work equals force times distance. So work equals force times distance. Now, work is W, we list it here. F is our force, and then D is our distance. So work, the problem tells us, hey, we want to know how much work is being done. And then the force, remember that should be in units of newtons. Now, think to this. Think back to what the force formula was. The force formula was mass times acceleration, and the reason that we have to consider this is the only thing that we're given out of this is a 1,200 kilogram car. So what I'm going to do, I'm going to put mass times acceleration. And it may seem for a second that, hey, we can't solve that, but we actually can. So our mass is 1,200 kilograms, and then this is the part that you may not think you have, but the acceleration. We're talking about a car on Earth. We haven't sent a car to Mars yet, and so what we need to do here is we need to multiply it by the acceleration due to gravity. So I'm going to put a side note right above 1,200 because it is being pulled down at an acceleration due to gravity of 9.8 meters per second squared. So my acceleration actually is 9.8 meters per second squared. And so all I'm going to be able to do here to solve for force is this. I'm going to put 1,200 times 9.8. I press enter, and I get 11,760 newtons. So 11,760 in 4 newtons. Now the distance, that mechanic lifted the car 0.5 meters off of the ground. So that becomes our distance of 0.5 meters. Now, I'm going to plug everything in the work formula. I'm going to do it down here. So work, W, equals our force, which we just took the time to calculate, which was 11,760 newtons, times our distance of 0.5 meters. So our distance is 0.5 meters. Now all I need to do in my calculator is take 11,760 times 0.5. So 11,760 times 0.5. And what I'm going to do, I am going to round this to 5,000. I'm just going to keep it 5,880. And remember, that is in the unit of joules. So we kind of had to think outside the box there a little bit, because at first it may seem like we don't have that particular setup, but we actually do when we piece together things and knowledge that we've already learned. So now we can transition to a very relatable topic, and that topic is power. And really, work and power can be used together, or they have to be used together to find out the things that need to be found. So the first thing that we'll start out here is just the definition of power. Power is defined as a quantity that measures the rate at which work is done or energy is transformed. So again, how power is related to work, it is the rate at which that work is done. Now, the key thing here, power is the rate at which work is done, or how much work is done in a given time. Now, power has the formula of P equals W divided by T. And I'm going to call power equal to W over T here. Now, the P for power is expressed in watts. The W is standing for work, which is expressed in joules. The T is time, which is expressed in seconds. Now, what we have to consider in the power formula is the time factor. So the shorter the time taken to complete work, the higher output of power. And on the flip side here, the longer the time taken to complete work, the lower the output of power. All right, so again, the time factor does affect this particular calculation. So now let's go ahead, let's talk about the units of power. We have it listed here as watts, but we can go into a little bit more detail about these units of power. So number one, the SI unit, or the International System of Units for power, is the watt. Now, to think about what a watt is, or what the unit of a watt is, 1 watt is the amount of power needed to do 1 joule of work in 1 second. And that's really nice that it's in these word forms here, but let's put it in some number forms. That makes a lot more sense in my head. So 1 watt, one big W there, 1 watt is equal to 1 joule per second. Or we can also call 1 watt equal to 1 kilogram meters squared per second squared. And I take that back. I made a minor mistake here. This should be seconds cubed on the bottom here. I forgot to factor in that extra divided by a second part here with power. So 1 watt is equal to 1 joule per second, which is equivalent to 1 kilogram meter squared per seconds cubed. And that is a cube there, or 3. Now, with this, the symbol for watt is non-italicized W. So you have to be really careful with power and not confuse it with work, because work, which is a W2, is italicized when you see it typed. So again, when you see just a capital W, that's going to be for power, and when you see an italicized capital W, that's going to be for work. It's important to remember that as we go through this. Now, how we calculate power is very similar to how we calculate work, and the first thing is to write down the formula for power. Now remember the units that we went over on the previous page there, and express those in the correct units. Now, you need to, in step 2, determine the known values of the problems, and it's important here to include units. Step 3 is to determine any unknown values of the problem. Once you've figured out your known and unknown values, you just need to insert those into the formula for power. The 5th step is to solve mathematically to determine the unknown value. And then the 6th and very important step is to include units in your answer. All right, so let's go ahead and put these steps to the test in a couple example problems. So we'll switch gears here. We'll go to the example problems. And we have this. We have a student who weighs 565 newtons and walks up a set of stairs that has a vertical height of 3.25 meters. This all occurs in 12.6 seconds. We ultimately want to know what is the power output of that student. So what we're going to do here, we're going to write down the formula for power. And remember, P equals W divided by T. So we just list out all our variables like we have been doing. So we list out P, W, and T. Now, ultimately, the question wants to know, well, what is the power output of that particular student? So that's going to be our big question mark here. And then we have to think about our W. Now this W stands for work, which we just got done going over. So our work here is force times distance. And so because we don't have the work in joules specifically given, I'm going to put down force times distance. Now, our force, if you remember back, is expressed in newtons. And so this student weighs 565 newtons. So we can put 565 newtons in that location, and we can multiply it by the vertical distance of that set of stairs, which we had listed at 3.25 meters. So to find out the value for our work in joules, all we have to do is take 565 and multiply it here by 3.25. So I'm just going to put 565 times 3.25, and I get a decimal number, and I'm just going to put that in there. So I have 1,836.25, and remember the unit here for work is joules. And then the time. This student did this whole thing in 12.6 seconds. So we have 12.6 seconds. Now, we insert our values for work and time into our power formula, and so we get this. Our power is equal to 1,836.25 joules, all divided by 12.6 seconds. So in my calculator, all I'm going to do is I'm going to take 1,836.25 joules divided by 12.5. So 1,836.25 divided by 12.6, and I get a value of this, 145.7 and lots of decimals. Now I'm going to round this to 3 total digits. So my answer here is going to be 145 watts, or 145 joule per seconds. So my power output here is 100, and I should have rounded that, 146 would be our answer. So our answer would be 146, big W non-italicized, for watts. Now, this same student now is running late to class, and so they got to get up the stairs in 10.5 seconds. We ultimately want to know what is their power output. So again, we're going to use that same formula of P equals W divided by T, or work divided by time. And again, we want to know what the power output is for this same particular student. The power output is ultimately going to be our big question mark. The work does not change. It's still going to be force times distance. They're still going up that same set of stairs. So we can use 1,836.25 joules. So 1,836.25 joules is our work. And this time our time is going to be 10.5 seconds. So we go ahead, we just plug these values into our equation here. So P equals 1,836.25 joules, all divided by 10.5 seconds. So in our calculators, all we have to do here is put 1,836.25 divided by 10.5. We press enter, we get 174.8 and lots of other decimals. Again, we only want to round this to 3 total digits, so this would round to 175 watts. So power in this case is 175, big W non-italicized, standing for watts. Now again, just to emphasize here the time factor. This same student, just because they ran up in 1.1 seconds faster here, or excuse me, 2.1 seconds, they increased their power by almost 30 here. So very important here to remember that power has that time factor. Now what we can talk about here, kind of our third topic of this section, is what we have called machines. And machines really tie together work and power really nicely. So with this here, machines, our basic definition of a machine is anything that helps do work by changing the size of an input force, the direction of the force, or both. So for machines, they are going to change the input force by the following two things. The first thing is that they're going to either redistribute the work that we put into them, or they can change the direction of an input force. So let's think of an example here. And a great example of a machine is a jack lifting or getting lifted up by a car there. And so if you're unfamiliar with what a jack is, here they have a NASCAR race here. A jack, this gentleman here pushed down on this lever, and it caused this device up here, the lift, to lift up the car. So obviously the gentleman is not putting enough force in that for him alone to lift up the car. But what the jack does is allows that redistribution of that work that's being put in, and allows you to multiply the amount of work that is actually done. So what actually happens here is that the jack makes the work easier by allowing you to apply less force to any given moment, or at any given moment. So to put this simply here, what that jack does is it's going to require the same amount of work to be inputted as lifting the car by hand would. All right, so let's get a little bit more into what machines can actually do instead of just giving this broad picture here. So we mentioned here that they can change the direction, and that's really what we talked about here initially. But let's talk about multiplying the force and how a machine can actually multiply the force that is given in this scenario here. So machines can also make the force greater by decreasing the distance by or over which the force is applied. So again, machines can also make the force greater by decreasing the distance over which the force is applied. So let's think about this as our example we have been in the jack lifting a car up. So what's happening here is that a jack makes lifting a car easier by multiplying the input force. So what's happening here, the detail wise with the jack, is that the structure of the jack, the way that handle works as you push up and down on that handle, it allows that lift to be or makes the person using that lift apply less force at any given moment. All right, so let's apply some mathematical concept to this whole business of the machines, or what they allow us to do. So mechanical advantage here, we're just going to start out with a definition, and this is a quantity that expresses how much a machine multiplies the force or the distance. So what this is in common term here, it's a ratio between the output and input forces. Or if we're talking about distance, it's the ratio of input distance and output distance. Now that ratio with the distance there, you have to ignore friction, which we're not going to factor in. Now the formula here for mechanical advantage is this. And I'm going to express mechanical advantage as MA. So if I bring this down here, we can call mechanical advantage MA. And so the formula here is this. There's actually going to be two formulas. Our mechanical advantage is going to be equal to this. The output force over the input force. Or if we're talking about distance, our mechanical advantage, so again, MA for mechanical advantage, is going to be equal to, we have to be careful here, the input distance. So input distance here, input distance, divided by the output distance. Now, let's talk a little bit about mechanical advantage. There is no unit because mechanical advantage is a ratio. So now we need to talk about the actual value of mechanical advantage. So the first value I want to talk about is if the mechanical advantage is greater than 1. If the mechanical advantage is greater than 1, we are going to multiply that input force. Now, something or a machine with a mechanical advantage that has greater than 1 is going to help you lift or move a heavy object. Now, if the mechanical advantage is less than 1, there's some different things we have to talk about. What a mechanical advantage of less than 1 allows us to do is increase the distance and speed of some moving object. And so what something within a mechanical advantage of less than 1 would do is it's going to reduce the force required to move an object. And so a great example of a mechanical advantage, or something that has a mechanical advantage of less than 1, is a ramp. A ramp, you have to walk up a lot longer distance, but it reduces that force of which is applied to you, and it just spreads it out over a longer distance. So let's go ahead, let's try a couple of problems, or just one problem on mechanical advantage. So we'll switch gears here, and we'll move to mechanical advantage, our problem here. Okay, so a person uses a claw hammer, and that's just like a regular hammer, but the claw part, remember, is like the spikes that allow you to get the nail out of a board. And so a person's using this claw hammer, and they have a force, they put a force of 15 newtons on that particular hammer. Well, the hammer, the way it's designed, gives that person a mechanical advantage of 5.2. We want to know how much force is exerted on that nail that person is trying to pull out with the claw hammer. So again, we go to our formula here, and now we have to be careful. So mechanical advantage, we talk about force, and we can also talk about distance there, like a ramp. But if we're given force in newtons, we need to turn to that mechanical advantage that uses force. So with that problem here, it says here the output force is divided by the input force. So all we need to do here is we're just going to plug in some numbers here. We're going to have our mechanical advantage, MA. We're going to have our output force, And we are also going to talk about our input force. So our mechanical advantage here, if we read in the problem, it's this unitless number, so that's given at 5.2. Now the output force, that is what happens or how much force is exerted after the machine helps us out a little bit. So right now we don't know the output force because it's taking our input force and it's using that in the machine and it's giving us a greater output force. But we do know that this person put in 15 newtons of force into that claw hammer. So all we need to do here is put these numbers back in and solve this mathematically. So we'll have 5.2 equal to our output force. We don't know how much output force we have yet, and this is all divided by 15 newtons. Now, remember, what we need to do here is we need to assume that these are equivalent fractions. So this would actually be 5.2 over 1. So we cross multiply. We end up with 5.2, and I'm going to write this down, 5.2 times 15 newtons. This equals 1 times your output force, or you could just put output force because anything times 1 is itself. So all we got to do in our calculator is put in 5.2 times 15. So we go through this here and we have 5.2 times 15. We press enter and we get a value of 78. Now that value would have a unit of newtons. So we put in 15 newtons worth of force, and because the way the machine, the claw hammer is designed, it gives us an output force of 78 newtons. Now the thing to be careful here is, are we talking about output force or are we talking about distance? Because that will affect your mechanical advantage problem that you use. Now let's talk about the mechanical advantage and ramps. We've talked about machines and tools and things like that. Let's specifically talk about a ramp and what that would do to give you a mechanical advantage. So with this, if we compare the amount of work required to lift a box onto the bed of a truck with the amount of work required to push the same box up a ramp. So let's get you this idea in case you can't picture it from words here. Let's say you're moving and you can either lift this box up to the same portion or the bed of this moving truck, or you can use that nice ramp and slide it up the ramp. Now notice here, the total distance is shorter when you lift it straight up, but if you spread that out over a longer distance on the ramp, your force is greatly reduced. So let's talk about moving the box straight up. Okay, so if we go back to this picture here and we talk about the box moving straight up, a total force of 225 newtons is required to lift that particular box. And the other thing to consider here with the box moving straight up is that it moves a total distance of 1 meter. So if we tie this all together with the concept of work, moving the box, which requires a force of 225 newtons, a total of 1 meter, requires a work of 225 joules. Now, let's talk about moving the box not straight up, but now let's talk about using this ramp to move that same exact box. So this time, because we have a ramp, we only have to put in a force of 75 newtons. So this time here, a total force of 75 newtons is required to move the box using the ramp. Now we input less force, or it requires less force here, but we have to apply that force over a total distance of the ramp, which is 3 meters. Now, when we think about the concept of work, which takes our newtons and multiplies it by our meters here, so 75 times 3, it's going to require the same amount of work, 225 joules, as moving that box straight up did. So again, this requires a total of 225 joules of work. So at the end of the day, both movements of those boxes, that same box, requires a total amount of work of 225 joules. The big difference is how much force has to be put into that box to get it to that same point. All right, I know this has been a long episode. We went through a lot of information with power, work, and now mechanical advantage. But I hope you've enjoyed this episode. And as always, make sure you subscribe.